So in this session, we will be looking into variation of all the three types of conductance: conductivity or specific conductance, equivalent conductance, and molar conductance on dilution. On dilution or upon decreasing the concentration. We know as the dilution increases, that is as the volume of the solution increases, concentration decreases. So upon dilution of the electrolytic solution, what happens to this? All three types of your conductance we will be looking in this session. So first we will be taking about your specific conductance, that is kappa. So what is specific conductance or conductivity? It is defined as, it is the conductance offered by all the ions that is present in 1 ml or 1 cm cube of a solution. Think that we have a container. This is a container. So you have 1 ml of solution. 1 ml of solution. Think that there are 4 ions here. There are 4 ions here. So 1 ml of solution. As a result, the conductivity offered by this solution is called as your specific conductance or conductivity. Now, what I am making is, I am diluting this solution, that is I am adding say 10 ml of water. I am adding 10 more ml of water. So what happens to the volume? The volume increases. Volume increases. So the volume, as the volume increases, the total number of ions per 1 ml will decrease. That is, the density of ions in 1 ml of the solution, electrolytic solution, decreases. So that is, after adding 10 ml of this thing, that is dilution, what happens is, the density of ions per ml decreases. As the density of ions, that is the number of ions per ml will decrease, which means that the conductivity will also decrease. That is because these are the ions. The ions are the things that are carrying the current in your electrolytic solution. Since these ions per unit ml will decrease, obviously the conductance, that is conductivity also decreases. So upon dilution, the specific conductance will decrease. Why? Because upon dilution, remember, the number of ions per ml of the solution decreases. As a result, the conductivity, that is your specific conductance, decreases. So I can tell your specific conductance is inversely proportional to dilution. The specific conductance is inversely proportional to dilution. That is, as in more you increase the dilution, the specific conductance goes on decreasing. So higher the dilution, lower is the concentration, hence the specific conductance also decreases. So this is about the specific conductance. Now what about your equivalent conductance and molar conductance? Both show the same pattern for dilution. That is, your equivalent conductance or your molar conductance show the same pattern of conductance for your dilution. Let us see what happens to this. So lambda EQ and lambda M upon dilution. We'll have a relation for lambda EQ and lambda M, and thereby I'll be telling what happens to this lambda EQ and lambda M. Say lambda EQ is equal to kappa into 1000 divided by normality, while lambda M is equal to kappa into 1000 divided by M. What is N? Normality, that is nothing but a concentration term. What is M? Molarity, it is nothing but a concentration term. Now let us see upon dilution. Dilution means you are adding more and more water. What happens to volume? Volume increases while concentration decreases. Remember this. Always upon dilution, total volume of the solution increases and concentration of the solution decreases. Which means that in your lambda EQ, normality decreases while in your lambda m, that is molar conductivity, molarity decreases. You can observe that lambda EQ is inversely proportional to normality, lambda m is inversely proportional to molarity, which means that if the normality decreases, lambda EQ increases. If molarity decreases, lambda m increases, which means that upon dilution, the concentration decreases while your equivalent conductance will increase. Molarity, concentration decreases and your molar conductivity will increase. So as a result, lambda EQ, that is your equivalent conductance and molar conductance, upon dilution, volume will increase, concentration will decrease, hence your equivalent conductance and molar conductance will increase, while that of your specific conductance decreases upon dilution, while these two will increase upon your dilution. Let us see the practical situation wherein why your lambda EQ and lambda m will increase upon dilution for two instances, for a weak electrolyte as well as a strong electrolyte. We will be explaining you why your lambda EQ and lambda m, that is your your equivalent conductance and your molar conductance increases upon your dilution. So this is just a relationship wherein you are correlating your equivalent conductance and concentration, thereby telling that lambda EQ and lambda increases upon dilution. Now we will be having a theoretical explanation why these two will increase by taking two instances, a weak electrolyte and a strong electrolyte. Remember this here, upon dilution, upon dilution, volume increases, concentration decreases. Your kappa, specific conductance, decreases, your lambda EQ and lambda m increases. So this is the gist of your discussion that we have done now. So now I am telling why lambda EQ and lambda m is been increasing upon dilution with respect to a strong electrolyte and a weak electrolyte. In the first session itself, we have discussed about what do you mean by a strong electrolyte and what do you mean by a weak electrolyte. So a strong electrolyte is an electrolyte which undergoes complete dissociation upon adding it to water. That is, say if there are 100 molecules of a substance, they get dissociated into, all the 100 molecules, they get dissociated into ions. So what do you mean by a weak electrolyte? It is an electrolyte wherein dissociation is incomplete. That is, if you have 100 molecules, they do not completely dissociate. Say about 10 molecules dissociates into ions, while the 90 molecules remain undissociated. Such a type of electrolyte is called as your weak electrolyte. So now let us see lambda EQ and lambda m, why it increases with respect to a weak electrolyte as well as a strong electrolyte. Say for example, I am taking a strong electrolyte, strong. So first I will take a weak electrolyte. First I will take a weak electrolyte, weak electrolyte. Weak electrolyte. So weak electrolyte is nothing but it's a substance whose dissociation is incomplete. In your first PUC, in equilibrium chapter, we have studied that upon dilution, the alpha of weak electrolyte increases upon dilution. That is, for a weak electrolyte, as and when you dilute it or as and when you add the water, the alpha is degree of dissociation, So you have studied this in your equilibrium chapter in your first PUC. Upon dilution, for a weak electrolyte, the alpha goes on increasing, which means that upon diluting more and more, the dissociation of your weak electrolytes increases, which means that they say 10 molecules have been dissociated in your water that you have added initially. Upon adding more and more water, diluting, all the 70 to 80 molecules that are present in your electrolyte gets dissociated, which means that the dissociation is more. As a result, the number of ions also increases. As a result, upon dilution, the weak electrolyte's conductivity increases. So upon dilution, degree of dissociation increases, which means that number of ions conducting increases. So remember, upon dilution for a weak electrolyte, degree of dissociation increases. As a result, number of ions conducting increases. So hence, therefore, conductivity increases. Conductivity increases. So this is why the reason a weak electrolyte upon dilution increases its conductivity. That is your, conductance, increases the conductance. It's not conductivity, conductance increases the conductance. So degree of dissociation, number of ions increases. Since the number of ions conducting increases, conductance also increases for a weak electrolyte. Strong electrolyte. So why the strong electrolytes conductance increases upon dilution? The strong electrolyte dissociation is already complete. That is, alpha is almost 100%. 100%. That is, the degree of dissociation is high. That is, all the ions have been produced once you add the electrolyte to your water. Then what is the matter of diluting it, which increases the conductivity of this electrolyte? There are two things which come into picture. The first thing is, upon dilution, the volume of the solution increases. The total volume of the solution increases. So volume increases. As a result, say this is a cation and this is an anion. You have a cation and an anion. This is a strong electrolyte. Since they are closer to each other, there is a force of attraction acting between them. So you have a strong electrolyte, a cation A, a cation B. It has some force of attraction when it is present in your aqueous medium. Now what are you doing? You are increasing the volume. As a result, these two ions move far apart like this, far apart. As a result, there is no intermolecular force of attraction between the ions. This frees up your ions to move easily. Movement of easy ion, that is easy movement of your ions, makes the conductance enhanced. So this thing is before dilution. You have some interaction between the ions. This is after dilution, wherein volume is increased. There is no force of attraction between the ions. As a result, they are free to move. Hence, the conductance increases. So that's your first thing. That is, the increase in volume decreases the force of interaction between the ions. The second thing is, the total volume, that is upon dilution, since the total volume increases, the mobility of the ions increases. Mobility of the ions increases. Simply thinking that these ions can move very freely because you have a large total volume upon dilution when compared to your before dilution. As a result, using these two things, I can describe that the strong electrolyte upon dilution also increases its conductance. That is, one is due to the low interaction, this total volume increases, the interaction will decrease between the ions, which will be present in the higher concentration electrolytes. The other thing is, the mobility of the ions also increases. Due to these two things, the conductance of strong electrolyte also increases with the dilution. So first, weak electrolyte, what happens upon dilution? Degree of dissociation increases. As a result, number of ions produced is more, conductance increases. The second thing is strong electrolyte also increases its conductance upon dilution. What are the reasons? Two reasons. The force of interaction between the ions decreases, as well as the mobility of the ions also increases. Hence, the strong electrolytes also conduct more when compared to your, that is, they also conduct more upon dilution. So, as a result, even strong electrolyte and a weak electrolyte upon dilution increases its conductance. That's your molar conductance as well as your equivalent conductance. Comparing the conductance of a weak electrolyte, increase in conductance of a weak electrolyte and increase in conductance of a strong electrolyte upon dilution, which is at a more extent. That is, whether the weak electrolyte increases for a more extent or a strong electrolyte will increase at a more extent. So, we will have a graphical representation for this, describing whether weak electrolyte increases its conductance to a more extent or a strong electrolyte increases its conductance to a more extent upon dilution. So let us see a graphical representation to describe this. So we are having a graphical representation to show that whether a weak electrolyte or a strong electrolyte whose extent of conductance increases upon dilution. So I have taken a x-axis lambda m, a y-axis lambda m, that is your molar conductance, and your x-axis is your root C. I have not taken your C concentration, we have taken root C in order to get the plot, a straight line for your strong electrolyte. So this is your plot wherein we are describing what is the extent of increase in conductance for a strong electrolyte and weak electrolyte upon dilution. So for a strong electrolyte, I am taking an example of KCl. KCl is a strong electrolyte I am taking. Electrolyte. So I can observe a plot like this. A plot like this, a straight line. A straight line like this, of not of much slope, which means that the conductance of KCl increases upon dilution but not of a much extent. That is, the extent of increase in conductance of KCl upon dilution is not of much. That is because once you take KCl and add it to water, all the ions will get dissociated. As a result, it will conduct, say, some X conductance it is having. Upon dilution, the conductance, the increase in conductance is very, very small to a small extent because there is no more ions to be produced. That is, already all the dissociation has been happened and there is no more ions to be produced. As a result, the extent of increase of conductance for KCl or a strong electrolyte upon dilution is very less. You can observe here. So this is the extent of dilution, but you can observe the increase in conductance is very small. So you can observe the dilution extent. Remember, from right to left we are diluting it, that is the concentration becomes 0. Here it becomes 0. Say this is about, say, 0.02, say this is about 0.04. So good, concentration decreases, dilution increases from right to left. You can observe for a vast dilution of this much area, the decrease in the increase in molar conductance is only this much, which shows that for a strong electrolyte there is no much variation of conductance upon dilution when compared to a weak electrolyte. So there is a very small extent of increase in conductance for a strong electrolyte upon dilution. Now let us see for a weak electrolyte. What happens to a weak electrolyte? So I will take the weak electrolyte as acetic acid, CH3COOH. This is a weak electrolyte. Weak electrolyte. So for weak electrolyte, we have already studied that upon dilution, the degree of dissociation alpha increases very sharply, which means that the acetic acid initially on adding to water, the number of ions produced is less. Upon diluting, what happens? The number of ions will increase at a very faster rate, which means that the conductance upon dilution for an weak electrolyte is more when compared to your strong electrolyte. That is, upon dilution the curve goes like this. Like this. You can observe, if this is the dilution, this is the dilution extent, you can observe the extent of increase in. So this is the extent of increase in molar conductivity. So if you observe your KCl, it is only this much. So if you observe this one, this is only for your KCl, only this much upon dilution, vast dilution. For acetic acid, you can observe the dilution is this one. So this is your dilution for acetic acid, while this is your dilution for KCl. This is your KCl, this is your acetic acid. So you can see a steep curve of your increasing molar conductivity of acetic acid, which shows that weak electrolytes conductance increases sharply upon dilution, while that of a strong electrolyte will be increasing but to a very small extent when compared to a strong electrolyte. As a result, upon dilution, weak electrolytes conductance increases sharply while strong electrolyte conductance increases but not as much as your acetic acid, that's your weak electrolyte. That is because it is having a complete dissociation initially. This upon dilution goes on dissociating, that is the alpha becomes increasing for only for your weak electrolytes. So this is what the extent of increase in conductivity for a strong electrolyte and a weak electrolyte. This graphical representation is very important. It will be asked for your final exams. Write a curve, that is root C versus lambda m curve for a weak electrolyte, root C versus m for a strong electrolyte. So as a result, keeping in mind your board exams, this graphical representation is very important. Remember, it's a graphical representation of lambda m and root C. For a weak electrolyte, you have a steep curve like this. For a strong electrolyte, you have a straight line with less slope. So as a result, this is your graphical representation.